Hi, I'm Gregory Haley, and I'm here today with Harry J. Levinson of HJL Lithography, and we're going to be talking about the current state of high numerical aperture or HighNA lithography. Welcome, Harry. Can you give us an idea of where HighNA is right now in terms of its development?
Well, it's being developed on many fronts. First and foremost is the exposure tool. There is an HighNA EUV tool that is fully assembled at ASML. They use a modular approach when they build their tools. So each of the subsystems, the wafer stage, the reticle stage, the optics, which would have been taken care of at Zeiss, all those have been tested as separate modules, and now they've been integrated together. And this is where the real hard work starts, trying to get the machine to really work in an integrated fashion. In my conversations with people from ASML, things seem to be moving along pretty well, and that's one part of it. There are many other parts of the technology that people are developing, the resist materials in particular. Those have been problematic for low-NA EUV lithography and have really gated progress to a certain extent. So work will continue, I'm sure, in trying to improve those and enable resolution at smaller features. We're sort of in a situation where the resolution is, of course, gated in part by the resolution of the optics, but we're sort of victims of our own success. We've now made the features so small that what's going on at the molecular level, the size of the molecules, has become important. So resist materials, that's very much a challenge. There are some other things happening along the mask front. People are looking at alternative absorbers, sort of the EUV equivalent of attenuated phase shifting masks. And that is one that's kind of interesting. A number of materials have been identified, but their use is complex. Unlike optical lithography, where we could get sort of one mask blank, one size fit all, we could do line space patterns, contacts, posts. We could do different pitches and dimensions, and pretty much all with the same mask blank. The simulations we've seen to date suggest that the optimum mask blank for what they call low N, sort of the equivalent of, again, attenuated phase shifting masks. The optimum is dependent upon the application. It can be different for line spaces versus contacts. It could be pitch dependent. And if you change the material from which you make it, sort of the optimum phase actually changes. Nothing about EUV lithography has ever been easy. And certainly going to a higher numerical aperture doesn't make it easier in a lot of ways.
What is it about the higher numerical aperture that creates the particular challenge with HighNA?
Again, just the fact that we're making smaller features is one. So that is one aspect. And as I said, there's a lot of materials issues there. You also have a depth of focus problem. That is to say, you need to maintain a separation between the lens and the top surface of the wafer to a very tight extent. It's something like on the order of plus or minus 10 to 20 nanometers, which is quite challenging, both at the level of the exposure tool itself. It has to have a very capable leveling system and focus detection system, exceedingly flat wafer chucks. We also need to have very good things like chemical mechanical polishing, what goes on the wafer. The chip companies who actually make the wafers have to ensure flatness to an extraordinary degree. So that's something that just is predictable just by going to higher numerical aperture. We always lose depth of focus when we go to higher NA. Probably another challenge that's unique to EUV's move to high NA is the fact that we now have a smaller field size, at least for the initial generation of technology. ASML, and correctly, in my opinion, decided to go with a higher lens reduction in one of the axes, and the mask size was not initially changed, which means now the field size on the wafer is half of what it used to be. So if we want to make very large die, we'll have to stitch it. That is, you print one half of your chip with one mask, then bring another mask in and expose that. And you need to make sure that everything lines up at the boundary. As we say, we stitch them together at that boundary. So that's one aspect that's very unique to EUV high NA. We didn't encounter anything like that in going to higher NA in optical lithography. Another problem, though, of course, is with half of the field size, you end up with a throughput challenge. You now have twice as many exposures on the wafer. So that will hurt the throughput. It's going to make it very challenging. Moreover, because the lens reduction is higher in the scan direction, in order to be able to have the same wafer scanning speed, now the reticle has to scan twice as fast as it did on the lower NA systems. It's the classic Red Queen's dilemma, right? You have to run as fast as you can to stay in the same place. And, you have to go faster than you can to get anywhere. So those are, I think, some of the very specific challenges having to do with just it being high NA.
What about the size of the machine? I know that the current EUV machines are quite large. Is this going to go up another factor of size?
Oh, they're much bigger, and it's just extraordinary. I think the real issue, though, is really the cost. The word is around $350 million a piece, but it's also very, very precise components. The lens is just fantastic. What Zeiss is accomplishing there, the level of precision that ASML is targeting to achieve in its positioning of the mask and wafer is really phenomenal. A lot of engineering has to go into these very sophisticated systems, and therefore it becomes costly. That really stresses the throughput issue even more, because you have to have very high throughput to recover your investment in the capital equipment.
Is the throughput with the high NA machines going to be equivalent to the EUV machines, or do you think they'll be slower?
With the smaller field size, they're going to be very challenged to get the same level of throughput as they have even today with the current low NA tools. Now, one thing they've done that is also extraordinary is that it seems they are removing one mirror from their illumination optics. And that basically means that with a given light source capability, they can now get twice the amount of light to the wafer. And that's a very significant improvement, and can lead to better throughput and also help to address things on the materials side. I think part of the reason we struggle with materials is with EUV, with the weak light sources and the need for high throughput, people try to go to the lowest exposure dose possible. But then you're always flirting with photon shot noise, which often looks a lot like some of these molecular inhomogeneity problems. So having more photons will definitely be beneficial on multiple fronts.
Will they be using the same source generation for the plasma beam? Will it still be the same equipment there, or will that also be upgraded?
I don't know the schedule that ASML has for the using this different illuminator with fewer mirrors. That may not show up on the initial tools, but could come a little bit later. And there are people around the world who are looking at potentially very powerful light source using what's called a free electron laser, and that could possibly show up in the future as well. There's a whole lot of work being done on the sources to try to get power up from the current laser produced plasma sources and also go to very significantly different alternatives.
I know that floor space in fabs is particularly precious, and with these much larger machines, do you feel like, or do you anticipate that the new High-NA machines will be going in just to the newer fabs, or do you think there will be some retrofit?
I think it will probably be fabs that were designed initially to take these tools because of their size, they'll have a certain weight that some older fabs may not be able to support. They also, with the need for very precise mechanical motion, will have to have exceedingly low levels of vibration and so forth. And again, I just don't know if some of these older facilities meet the specifications. But ASML has provided chip companies with the requirements, I think, some time back. Companies like TSMC and Intel and Samsung and so forth have had quite a bit of time to ensure that their newest facilities will have the capabilities on the facility side to support High-NA.
Do we have a sense of what the dimensional difference will be in between the two, the low NA and the High-NA EUV? What is the scale difference for
in terms of the feature sizes being printed?
Yes.
Well, today, people are patterning, something on the order of 16 nanometer half pitch with single exposure, whereas the High-NA tool is targeted for half that feature size.
What about the middle of the line process? How much of that has to change to account for what High-NA is doing differently?
In terms of the integration, I'm not certain that there's a lot that's specifically driven by the High-NA. Concurrent with this move towards the higher NA systems, we do have evolution in the transistor itself. And that's something that's, I think, happening independent of the lithographic capabilities. So we're moving to these gate all around types of devices, and then there's variations on that. So there's something called a fork sheet, which allows one to pack these gate all around structures tighter. And then there's to go to complementary structures, so-called, where the N devices and P devices are stacked on top of each other. So you get a significant area savings for CMOS technology. So that's all happening in parallel, and that is being developed with the larger feature sizes with the current lithographic capability. But all that, it's a matter of shrinking and what takes place. But I think the main integration changes just come from this transistor, at least in the front end in the middle of the line. The back end, on the other hand, is very much challenged because of, and to some extent, the middle of the line as well, because of electrical resistance. We for a long time, we have not seen the transistor gate pitch scale at the same rate as in the past, because you need to fit a contact in between those gates, and we can't make it very, very small or it's too resistive. So the fact that we have capability to make things smaller is going to certainly be pushing people to come up with better contacts, better wires, things with lower resistance.
ASML and IMEC are developing a pilot line on the High-NA pilot line in the Netherlands. Do you know where they are in development of that?
They're going to need to build a tool for that. I do not believe it's the current tool that is being fabricated, but it'll have fairly basic amount of equipment, resist processing, of course, and then metrology. the expanded part of that is to make use of IMEC, which is just, I don't know, I guess a couple hours drive from Veldhoven to back to IMEC in Leuven, and additional wafer processing can be done there. So it's kind of an extended lab, and it'll have a lot of people involved. So very top flight people. So I anticipate that a lot of exciting information will come out of there.
At Semicon West, ASML mentioned that they were anticipating first light on their HighNA systems later this year. What will they be looking for in terms of development at first light? What will be the primary challenge for them there?
It's again back to the integration. You can make a wafer stage and have it scan very, very nicely. You can have a reticle stage and have it scan very nicely. Now these two have to be scanning synchronously and very, very high precision. You need to have them going in the right directions. They have to scan in parallel directions and that type of thing. And you need that for good imaging and for good overlay. The other thing to point out is that the initial lens they've installed is not a high resolution lens. Zeiss does need additional time to make a super high quality lens. So they made one that's good enough to get decent images for initial debugging. It allows them again. There's a lot of mechanical aspects to the lenses, all these manipulators and things like that, corrections for heating and so forth, and they can test that out with the current lens. And then at some point they'll finally get a very high quality lens from Zeiss, and I'll have to swap them out at that point.
And what node will HighNA be implemented?
The nodes naming always becomes a struggle these days. But right now, people are trying to print 12 nanometer half pitch. Right, and they're doing it, but they're using multiple patterning. So I would not be surprised that if initially they may just wish to go to single patterning to get some simplification there, and then progressively go to smaller feature sizes. But what I find really remarkable is the amount of confidence that people have. There's been discussion of even going beyond HighNA to what's referred to as HyperNA. So every problem I talked about, the small depth of focus, cost, all these things, these don't go away by any stretch of the imagination. And not only that, we'll definitely, I'm pretty certain we would need polarized light if we went to the HyperNA, which is not something that it's certainly not needed at the low NA. You might want to have it to really squeeze the last out of the high NA optics, but it becomes pretty much a necessity at the HyperNA.
Can you describe what polarized light is and what the challenge is for that?
It's electromagnetic radiation, and it's the electric field points in a direction. It propagates in one direction, but the polarization vector is perpendicular to the direction it goes. Now, in normal light that you just get in a room, the light is unpolarized, which means that electric field could be pointing, 360 degrees around the direction of propagation. In order to get really high contrast, when you go to these larger NAs, you need to have the polarization vectors all lining up. We could take the non-polarized light and polarize it, but you throw away 2/3 of your light. The free electron laser is intriguing because that could produce directly polarized light.
Well, the prediction is that we'll begin seeing HighNA production in 2025, maybe 2026. Do you think that's realistic?
I'm skeptical of 2025 in the sense of, if they first get their tools up and running in this lab, things really working in Veldhoven next year, then they'll need some time for further debugging, which means they'll really start producing tools in 2025. And I have no doubt that they'll have shipped by somewhere 2025 at least one or two exposure tools to the big companies. But to do high volume manufacturing, you need more than one or two tools. 2026, though, on the other hand, is more pretty realistic, I think.
Many of the new fabs are developing. I know in Ohio, they're talking about being ready by 26 or 27. The new Arizona fab, you're talking about 27, 28. So it seems like that lines up with where they'll be in terms of production.
Yeah. Yeah, it's just, just things take time. And even when they all work well, if they run into some snags.
All right, Harry, thank you very much for your time today. I really appreciate your insight and knowledge, and I'm sure our viewers will enjoy it as well. Looking forward to speaking with you again soon.
Okay, well, thank you very much.